Hello everyone, today we're going to take a look at a pretty simple mechanics question that deals with inclined planes, friction, and most importantly work. Let's introduce the notion of work or just review. If you already know what is work, then we're just gonna refresh our memories and keep rolling. So the work is denoted as W here, is equal to the integral of F times dr, where dr is the infinitesimal distance. This is a vector quantity, and F is like a force. We all know that. So what does this really mean? It's basically saying that if say you are holding an apple, that's your basically hand, whatever. Here's the apple. You're holding it in your hands. And you are lifting it up with a constant speed. So V is C, where C is constant, which means acceleration is 0. You're moving it up 3 meters high. The apple weighs, say, 2 kilograms. How much work do you do? Well, here, look, we don't take really the integral because this example is quite straightforward. You don't really need to do too much math here. Basically, you need to find the forces here, and then you need to multiply that force that moves the object up by the distance, which is 3 meters in our case. So what is the force here? Force is not negative, it's positive because it's helping the motion. We're gonna talk about it later, just in a second. Well, force here is mg, h, that's gonna be work because h is the distance that it moves. For now, let's just focus on force, and let's get rid of h here. So force is equal to mass is 2 kilograms. The force of gravity is, say, 10 meters per second for the purposes of this analysis. So 10, this is 20 newtons. And then work is force times the distance. So 20 times 3 gives us 60 joules. Joules is basically the unit that we use for work. Technically, it should be newtons times meter, but that's just joules. That's a very simple overview of work. We're not diving into the conservation of mechanical energy, which is kinetic energy at point A plus potential energy at point A is equal to kinetic energy at point B times kinetic energy at point B, and we're not really talking too much about the kinetic energy or potential energy here, which is also denoted PE or U. This is negative, but it depends on the reference frame. We're not going to be talking about any of that because the problem basically tests our very fundamental understanding of W, which is what is work. Again, remember that it's as simple as the force that you apply on the object and the distance that it travels. As simple as that. Just work times the distance. That is your work. That's the definition of work. Now let's get into the question. A box slides down an inclined plane. Inclined angle is 37 degrees. The mass of the block is 35 kilograms. The coefficient of kinetic friction between the box and the ramp, this is mu k, is equal to 0.3, and the length of the ramp is 8 meters. Here they give us a little diagram. So the box is sliding down, it's pretty clear. Does it have the acceleration? I'm not sure, they're not really talking about it. Probably it does, but it might well have a constant velocity. But I think that there is acceleration. Anyway, so it slides down. We have the distance. This is this whole length of the inclined plane. Then we have mu k, which is the friction coefficient. Let's write it down just as a reference sheet. Then we also have d is equal to 8 meters. All right, the questions. How much work is done by gravity? how much work is done by the normal force, how much work is done by friction, what's the total work done. Let's draw a free body diagram. It will be much easier. I'm actually going to copy this setup and I'll paste it right over here. No, let me paste it. Copy, paste. Can I make it a bit bigger? No. All right, that's fine. So what forces do we have? Obviously, we have the force of gravity, mg. We have the normal force. Oh, I'm sorry. We have the normal force perpendicular to the surface that the object is sliding on. Then we have the force of friction. Oh, that's not a straight line. That's not a straight line either. That's fine. So the force of friction, it's kinetic friction. Let's denote that. And those are all the forces acting on the system. But I'm gonna break the force of gravity into components. That's the most convenient way to deal with this question. So this 37 degree angle is the same as this 37 degree angle. So the vertical component of the force of gravity will be mg cosine 37 degrees. And the horizontal component will be mg sine 37 degrees because it's opposite to the angle. SOHCAHTOA, remember? And now let's just draw a free body diagram. On your real tests, you can't really draw this kind of free body diagrams. I'm just drawing it for myself for convenience. On the real test, you will need to draw for the free body diagram like that. Basically, then you have your gravity there. But for my convenience, I'm going to denote all the forces and their x and y components. So here's normal force, here's force of friction. Here I have the y component of the force of gravity, cosine 37 degrees. And here's the horizontal x component. All right, what's the first question? How much work is done by gravity? Look, we're not considering this gravity because it doesn't really play any role. I didn't really touch upon this important concept before, but basically imagine that you have a big block here and there's like a human trying to push this block as hard as they can, or pull it with a string, whatever. They're pulling it with a string and it accelerates to the left. The work done, the total work done in this situation will be the force of tension. Now look, it will be the work done by the human, let's call it W sub h, minus the work done by friction, because it's in the negative direction. And again, you see, we're not considering normal forces or the force of gravity in the y direction because they don't help, and they don't act against the motion. So they simply are kind of ignored completely in this analysis. I hope it makes sense. So if the force helps, then it's positive joules. If the force is against the motion of the object, then it's negative joules. If the force doesn't affect movement at all, it is just zero. The work done by that force is zero. Now, with all of it being said, let's move back to our question. How much work is done by gravity? So, part A. The work done by gravity will be the force of gravity, specifically in the x direction, because that is where the object is going. It's not going up or down, it's just sliding left or right. So let's denote it Fgx times the distance. So work done by gravity is equal to this value right there, mg sine 37 times d. So the work done by gravity is, well, mass, they told us, is 35 kilograms. Let's assume that g is 10 meters per second squared, then d is 8, the length of the ramp, and sine 37, give me a second, sine 37 gives us 0.6, so this is all equal to 1680 joules, or Newton's time meters, but let's just ignore that for a second. Let's just say it's joules. Then part B, how much work is done by the normal force? Okay, does normal force play any role in the movement of the object? Does it help or resist the movement of the object? So if we have the box here, does it move it to the left? Does it move it to the right? No, it doesn't. It's just staying in the equilibrium with the force of gravity in the y direction. So here, the work done by normal force will be 0. All right, the part C. How much work is done by friction? Ooh, okay. They gave us the friction coefficient, remember? Mu k is 0.3. First, let's find what is the force of friction. It's basically the coefficient of friction times the normal force. And the coefficient of friction in our case is 0.3. The normal force is equal to the force of gravity in the y direction. Because if it were not to be equal to the force of gravity, then the object would either go up or go down, which is clearly not something that's happening here. Oh gosh, I am really sorry. So 0.3 times m is 35, g is 10, cosine 37 is, I am pulling out my calculator, it's 0.79. So all of it is going to give us 0.3 times 35 times 10 times 0.79. This gives us basically 83 joules. No, this is newtons, sorry. This is just the force. We haven't touched the work done by friction yet. So the work done by friction is equal to the force of friction times the distance. The force of friction is 83 and the distance is 8. So that is equal to 664 joules. And the last part, D, probably the most interesting one, is what's the total work done? Well, as we discussed before, the work total is equal to all the forces and all the objects that do the work need to be summed up so that we find the work total. It's much similar to the net force. You know, net force, if you have, I don't know, like applied force, then you have the normal force, then you have the force of friction, which is probably going to be negative in this case. That's the same thing with the total work done, or we could also call it the net work done. So the object clearly slides down leftward, and the main reason why that is happening is because of the x component of the force of gravity. So Vg plus, are there any forces acting against this motion? Of course, the force of friction. So we're going to say plus negative work done by friction. Now from here is just simple maths. the work done by gravity, we calculated it's 1680 joules plus negative work done by friction. It actually should have been negative from the very beginning. I mean, the force is not negative, but here it should have been negative. So what's the final answer? It is 1016 joules is the total work done by all the forces and all the items that do the work in our system. I hope that this lesson really helps. I hope you took away something really valuable from this little problem-solving session we had. And if you have any questions, please leave them in the comment section below, and I'll make sure to answer those. As always, thank you for your time, and I see you tomorrow.